Every day, enterprise financial systems process millions of transactions. Cash flows in, invoices wait, and remittance data floods the network at staggering speeds. The objective for any finance department handling this volume is simple: increase straight-through processing, or STP, where payments are matched and posted automatically, and reduce days sales outstanding. You want the cash applied accurately, and you want it fast. Look at the top tier of vendors tackling this. Names like HighRadius, Sarala, or Esker. They have built highly capable systems organized around a shared core strength: advanced optical character recognition and AI document understanding. This flowchart breaks down the architecture almost all of these platforms rely on. It's a linear 15-step pipeline. Data is ingested on the left. The AI extracts the text, normalizes the payment, runs it through a matching engine, and if everything lines up, it reaches automatic posting on the right. When a customer pays exactly what they owe and includes a perfect remittance slip, this pipeline works flawlessly. Hundreds of clean payments bypass manual review entirely and post straight to the ERP. The system breaks when reality introduces friction. A client submits one payment to cover hundreds of invoices, but shorts the total by a few dollars. Or they omit the remittance advice entirely. Or there is a severe currency exchange difference. These complex variables hit the pipeline and immediately cause a bottleneck. Because this architecture operates on rigid Boolean logic, it treats these complex variables as binary failures. If a payment doesn't match perfectly, the system kicks it out of the automated flow and dumps it into a manual exception work list for a human to figure out. Approaching cash applications strictly as a linear document processing problem guarantees an operational bottleneck. No matter how good the OCR gets, this architecture places a hard, unbreachable ceiling on how much of the process can actually be automated. Viewed through a scientific lens, an unpaid invoice paired with a partial payment represents a specific state of mathematical uncertainty. To push straight-through processing past that ceiling, organizations have to stop relying on rigid rules engines. The solution requires treating cash application as a problem of probabilistic decision science. Here is the structural difference. On the left, we have standard logic gates. A payment either matches or it doesn't. On the right, the architecture changes to a Bayesian model. Instead of true or false, the system quantifies missing context across a multivariable probability graph, where connections strengthen as certainty increases. In a Bayesian paradigm, a complex short pay is no longer a failure to be discarded. It becomes a high-signal data point acting as an anchor, pulling in other floating variables like historical client behavior to calculate a likelihood. The AI's job shifts entirely. It is no longer executing a basic read and match task. It is actively orchestrating the progressive reduction of uncertainty, bringing the mathematical confidence score up until it crosses the threshold for approval. Standardized vendor platforms prioritize task automation, matching a line item, over full workflow orchestration. Because their models are designed for a broad customer base, achieving this degree of probabilistic orchestration requires building proprietary layers tailored to a company's specific business logic. Reframing cash application as Bayesian uncertainty reduction transforms the AI into an orchestrating agent, moving beyond the limitations of basic data extraction. This strategic shift from consuming standardized automation to building customized parallel machine learning logic is called domain engineering. To build it, you have to dismantle the traditional matching pipeline. We strip out the static rules engine and replace it with a three-dimensional stack of proprietary science models. At the base, we establish timing science. This layer maps the specific historical payment cadences of a client's customer base, factoring in typical delays or seasonal habits. Above that sits deduction science. This layer mathematically models the enterprise's unique trade promotions, volume rebates, and specific contract pricing logic that a generic OCR tool would never understand. The top layer is customer behavior science. It specializes in resolving complex parent-child corporate hierarchies, tracking how subsidiaries pay on behalf of holding companies, or how cross-company settlements are structured. These layers do not output simple true or false flags. They calculate independent probabilities simultaneously, aggregating their findings into a single mathematical value at the top of the stack. Building these layers in-house ensures absolute data sovereignty. the models are trained strictly on the enterprise's proprietary operational nuances, rather than being diluted by a vendor's general data pool. Domain engineering takes a process typically viewed as a commoditized operational cost and transforms it into a highly protected competitive differentiator. There is a distinct risk in deploying complex mathematical models. If finance teams cannot audit the logic behind a decision, they will mistrust the system and reject the automation entirely. Because of this, domain engineering requires a strict mandate for the user interface. The system must possess an explainable infrastructure. When the system flags a transaction for review, it does not display a generic error message. It leads with a calculated confidence score, quantifying exactly how close it is to resolving the item. Below that score is the decision path. The interface explicitly maps out the historical evidence it relied upon, showing what data points matched perfectly and exactly where the logic hit a wall. The system goes further than just identifying the block. It highlights the exact missing variable required to push the confidence score over the automatic posting threshold, like asking the user to verify a specific daily currency conversion rate. This level of transparency is absent in traditional SaaS tools. Those systems operate as black boxes, offering automated recommendations without ever revealing the underlying evidence that generated them. Presenting calculated uncertainty allows the human operator to pivot into strategic auditing, shifting their focus away from repetitive data entry. Explainable infrastructure is the non-negotiable bridge between complex probabilistic mathematics and actionable enterprise trust. To effectively interact with this architecture, the human operator needs a specific conceptual framework: mile-deep critical thinking. Mile-deep critical thinking is the practice of moving past surface-level data consumption. It requires the operator to rigorously interrogate the underlying assumptions of the AI's outputs. The first component of this practice is contextual synthesis. The human operator takes the AI's probabilistic findings and connects them to broader organizational goals or situational nuances that the algorithm cannot perceive. The second component is evidence validation. The operator leverages the decision path provided by the explainable infrastructure to independently verify the AI's logic against primary, credible sources. Applying mile-deep critical thinking ensures the enterprise does not blindly institutionalize AI hallucinations or embed biases carried over from legacy training data. Consider a massive multi-invoice short pay that stalls the system at a 70% confidence score. An operator using this framework investigates the missing variables, identifies a misapplied trade promotion, and inputs the correct context to clear the transaction confidently. This operational dynamic is what it means for a business to truly flex its AI muscle. It is the shift away from manual execution toward intelligent, automated orchestration. The true power of an AI platform is unlocked when high-level human intelligence is actively applied to interpret, challenge, and refine the algorithm's heavy lifting. The final and most vital component of the mile-deep critical thinking framework is reflective iteration. When a human resolves a messy case, that decision must feed directly back into the system. Here is how that feedback loop operates visually. The resolution flows backward, embedding specifically into the science layer that flagged the uncertainty. This human input updates internal model weights, permanently altering how the platform calculates future probabilities for that customer's behavior. The machine's neural logic restructures its weights in real time. High-quality human input actively refines the system's analytical capabilities. In traditional tools, a human correction merely bypasses the system to get the payment processed. The underlying logic never improves, and the system will fail the exact same way tomorrow. With a continuous learning loop, the platform gets smarter with every resolved exception, progressively and permanently raising the theoretical limit of straight-through processing over time. This creates a perfect overarching symbiosis for the enterprise. The AI platform automates friction and scales analytical insight, while human capital is reallocated to high-level strategic curation. This is the reality of the buy versus build decision. Building a bespoke business AI platform is a long-term investment in proprietary control and deep differentiation, outlasting the short-term savings of an off-the-shelf product. Platforms like Buyflex.com exist specifically to facilitate this union. They provide the foundation to unite business strategy, functional expertise, and next-generation AI architecture. The combination of domain engineering and mile-deep critical thinking transforms cash application into a continuously optimizing proprietary decision engine.